name is Clay Mitchell. I'm with the company Revolution Energy, and with me is Dean Schenkel from Arateo. Together, we are the group of people that have put together the project that's taking place with the Exeter Region Cooperative School District. And one of our desires with this project is an energy project. And I'm going to go over the various aspects of the project and talk a little bit about the role that engineering plays in this project from start to finish. Start being 2 years ago, approximately, we started talking about this, and the finish being about 10 years from now, which is when the end of the project takes place. And one of the components of the project that we believe in making it important to both us and the school district is, since it's at a school, to somehow try to find out a way to make it something that if we find people that are interested in it, that you can be a part of the project. So naturally, the classes that we felt were the most important would of course be the engineering classes. We're working with the welding class and building sciences. We're also working with the computer programming class here at the SSD, and I'll explain that a little later. But the whole concept here, especially during this installation process, is that you all get an exposure to what's going on and you see what we did to get to this point. It's so that you can see firsthand what roles all the various engineering professions play in this. And so today is kind of like an introduction that we're giving to just the engineering groups, students, and also it's important for me that I hear from you what you would like to see over the course of the next 4 or 5 weeks while this project is going on, because once this stuff's installed, that's it. It's just sitting there and working. We can take things apart, and if I know what you want to see and who you want to talk to, I can make that happen. But if I don't hear from you, then I'm going to guess, and I could bore you to tears, and that's definitely not what I want to do. So we are working on a project that's at 2 sites. This is the building that we're in now. Obviously, this side is the SST side. This is kind of the middle section. I'm not sure if it has its own name, but collectively, they're called the Tuck campus. And then you probably all know this, the Exeter High School. So the project that we're dealing with confronts energy on both of these buildings. And we are addressing the problem in the Tuck campus is the heating system. And it was older oil-fired boilers, and here you can see a picture of one of the older ones after it had kind of fallen apart. And the nature of the system, because it's oil steam system, you get a lot of problems with balancing the heat. So I don't know if you've ever been in that old building over there, but on the second floor, and this picture was taken in February of 2009, so it was about 20 degrees outside. On the second floor, you get a lot of people's rooms are uncomfortable because it's really hard to control a steam heat system. It does a great job of heating it, and it almost makes it too hot in some places. So you have, even in February when it's 20 degrees outside, you have people who are opening their windows. And that's obviously not a very good way to heat your building. This picture was taken yesterday. This is the new boiler going in. So this is the sections. This is now, we're going from oil to brand new natural gas steam. And so these boilers are going to be much more efficient, and the project's happening right now. The way we talked about it and the way why this is such an important aspect for a lot of different people is not only are we replacing an old system, but we're replacing it with a very clean way to produce heat and power. And we come up with the way to measure it is how many tons of CO2 are you avoiding. Everybody's talking about carbon dioxide being a greenhouse gas, and it's also a good way to understand how clean your system is. So the way these 2 buildings used to work prior to our work and after, we're going to reduce the outputs of the buildings by 532 tons of CO2, which is the same amount of pollution put out by 107 cars.
107 cars over what period of time?
Per year.
Per year.
Yep. So we annualize the output reduction. So every year we're going to reduce it by 107 cars. So now we get to the technology. And the technology, this is kind of I'm going a little bit backwards so that you can see where we are, and then I'll tell you how we arrived to it. In the Tut campus, you have 2 heating plants in this building. There's one here where that chimney is, you can kind of see the shadow, and there's one here, and you can see the shadow of that chimney. That is the oil-fired boilers. This is some older boilers, but they're natural gas-fired. This building is heated by hot water, meaning in all the vents and in the air handlers, there's just hot water, so the temperature can go up and down. It's just a measurement of the heat of the water. This side is all steam, so that's one temperature, 220 degrees, and it's pressurized, and you can't really make the temperature go up and down. The steam is the temperature that it is, and you have to try and let it into the building, yes or no, to make heat, and that's where you get that craziness with people opening windows. If you walk around this building today, or if you walk around at any time in the winter, you won't see windows open because people can turn down their thermostats. It's much harder to do that in the other building, and so you'll see a lot of days where the windows are open and closed, and it kind of defies logic. Now, new boilers, natural gas. I already showed you a picture. In this room, where you're sitting in this building, we're going to put in a unit called a microturbine. And a microturbine is just like a big turbine that produces power, only this one's going to be about this big. The part that moves, it's a round cylinder about like that, and it is going to produce 450,000 BTUs of heat per hour, which is about 20 times the size of a boiler you would have or a heating unit that you would have at a house, and it's going to produce 65 kilowatts of electricity per hour. And the technology here is called combined heat and power. It's called that because you have one unit that takes one fuel and produces both heat and electricity. The way it works is just like a jet engine. The natural gas will come into the combustion area. The gas will combust. It'll spin a turbine. It'll eject the fired gas. They'll pull heat off of that. And then when the exhaust pipe goes up through a hood, that exhaust pipe will also have heat capture devices on it. And all that heat will go to heat up water, and then that water will be distributed through this building. And so you have a unique, it's not new tech, it's a new way of doing an old idea. Way back in the 1800s when they started building the first power plants, they were all combined heat and power. And you would have steam lines and electric lines coming from power plants, and people would heat their buildings from the steam from the power plant. And that's a much better way of doing things because you get all of that extra energy from that one fuel. On the high school, we're going to put a solar array. This was our first artist rendering, and I'll talk about that a little later, but this just shows you the scale. This is the building. This was one of the installation locations we were looking at early on, trying to make an element visible. Because we used this image, we didn't have the windows, so obviously we can't do that because it would cover the windows. Some of the fun things you'd learn when you're doing a project. Why solar? This is a brand new building. The heat plant doesn't really need to be replaced, even though it unfortunately has to burn oil because there's no natural gas line out there. There's really no other alternative right now that would provide a significant amount of savings. And it's brand new equipment. Replacing brand new equipment doesn't make a lot of sense in a lot of cases. So what we focused on was the electric load of this building. And so what we're going to end up with is the largest solar array in the state. It's going to start out at 75 kilowatts, and it'll go up in March of next year to 100 kilowatts. And so that's 100,000 watts. So you have a light bulb that's 100 watts. This is 100,000 watts of solar power. We will own it for the first 10 years. I'll talk about the nature of the project. The panels are guaranteed to put out a certain amount of power for 25 years, and 35 years is actually turning out to be less. Everybody is saying that the panels will last for 40 years. So when we put this up, the high school will have a portion of its electricity generated by solar for the next 4 decades.